Hey everyone, welcome back to DOCAS. Today we have Brad Dirks again from the University of Michigan, who's going to tell us about the shape of roots of D functions.
Yeah, great. Thank you for the invitation, or thanks again for the invitation to speak. Okay, yeah, so I think I'll begin with setting up the notation that we used last time, and also just describe a little bit of the results that we had last time. So the notation is I'm going to let R be the polynomial ring over C in n variables. I'll let X be spec R, which is really just C to the n. And I'll let D, which I'll probably sometimes write as dx, be the differential operators ring. And really this is just adjoining these partial derivative elements, which commute with the variables like this. I guess, yeah. So this is the Kronecker delta, and I guess they commute with each other. Maybe that's worth saying. Oops. Okay, and so last time we sort of built up all these notions we need from D modules for the proof that we're going to do today. So we talked about the characteristic variety of a D module, side changing, and we talked about push forward. So this is where pi is some map from y to x. Yeah, okay. And we considered this module NF, which was dxs times some formal symbol f to the s. This was sitting inside of R, and we invert f, and we also adjoin this variable s times f to the s. And remember, the action of the differential operators looks like, yeah, well, I'll just say how you do it. You extend it by the Leibniz rule to basically everything, but the way that this is like the power rule. So we bring down the power, we differentiate that function f. And since we want to write everything in terms of f to the s, we should just write everything as a coefficient of f to the s. And we need to divide by f. So really this is like s times dxif times f to the s minus 1, which is like how the power rule works from calculus. Okay, and we always make this assumption. So these are subsets of X. So I'm going to star it. So if we look at where all the partial derivatives of F vanish, this should be contained in the set of points where F vanishes. Okay, so these are as subsets of X. And this is always okay by, you can do something called generic vanishing. So use this theorem of generic vanishing on the source. And we can just throw out the points where like all of these vanish that aren't 0 on the source. And then we get some sort of open subset of this 0 set. And since we're talking about singularities, it's fine to replace all of X with just an open subset of this vanishing locus. Okay. And then last time we also showed, sort of like to finish it off, if F is quasi-homogeneous, so that meant like theta F equals F for some theta in this module, and satisfies star, then its B function or its Bernstein-Sato polynomial exist. And so remember that BF of S is minimal such that if we multiply it by the symbol F to the S, that's equal to some differential operator, which depends on S, times F to the S. So really F times F to the S, we should think of it as F to the S plus 1. Okay, great. So that was, oh, maybe I'll leave this up. So this is just a review of what happened last time. And so the goal for today is to finish the proof that BF of S exists in general. remember BF of S, we want it to be non-zero because we could just take it to be 0 and then it's a done deal, but we want it to be non-zero and monic of smallest degree, such that this functional equation holds. This sort of thing will be called a functional equation. So we'll prove the existence in general using a trick of Kashiwara, and then after that we'll describe a proof which was given initially by Kashiwara and then refined by Lichtin, and then my advisor Mircea Mustatsa and I applied that proof to more general elements of a certain D module to get more information about these Bernstein-Seto polynomials. Okay, so let's start with the proof of the general existence. So BF of S exists for any F satisfying star. So we keep the star assumption, but we drop the quasi-homogeneity assumption. And yeah, again, star is sort of a harmless assumption to add on to our theory. Okay, so what we do is we consider this function, f times t on x cross c. Actually, maybe I won't call it t because we'll do f times z on x cross c, where z is a coordinate on that c factor. Okay, so then t dt applied to f times t is just equal to f times t, right? Like the f comes out and then the t goes away, but then you multiply back by the t. So this is quasi-homogeneous and satisfies star. It's pretty easy to check that this function will satisfy star on this x cross c. And so that means
t is z. Is that right?
Oh, sorry, yeah, those are all z's, my bad. Okay. Yeah, I think it'd be confusing to use t because we also use t for this shifting operator. So z dz fz fz. Yeah, so this function is quasi-homogeneous and it satisfies this star assumption. And so that means that it has a b function. So I'll just say this exists. So it satisfies bs times t to the s f to the s equals some operator p of s times, I'm writing t again, z, and really I should put those all in parentheses, but it's going to be harmless to take them out. zf, I guess, times zf to the s plus, whoops, times zf to the s. Okay. But the nice thing about these differential operators, when you look at a product like this, is that everything involving z and dz is kind of on its own. Like if we looked at like d of x cross c, this is really just like dx adjoin z and dz in the way that like these two commute with each other like this. And so we could write p of s as like a sum of things, but actually, sorry, I want to let q of s be the like the homogeneous component of p of s of degree -1 in z, where z has degree 1 and dz has degree -1. Okay, so really what this means is q of s looks like, so it's a sum of a bunch of things. There's qj of s, where these are only differential operators on x, so they don't involve z or dz. And then there's some power of this t, z dz to the j. And then there's a dz extra term. Right, so using this commutativity rule, we can always sort of write it in this form. So we can make it where like the z and the dz are next to each other, and then we handle the next piece. And it has degree -1 because this part has degree 0, and this one has the -1. Okay, so we look at this, and then we really get right on the right-hand side, there's this extra z term. Like this is z, yeah. Yeah, I guess, so because of this extra z here, the only sort of equality that we really care about is going to be the one concerning this homogeneous component of degree -1, the one that gets rid of that z term. I should say, like, remember that because z dz is like the theta that recognizes this as a quasi-homogeneous polynomial, recall that z dz times this symbol zf to the s is just giving us s times zf to the s. So I think we talked about this that's like just from the differentiation rule. And yeah, so we really have this relation qs times zf to the s is equal to this bs zf to the s. And we can write this whole right-hand side, like applying the rules and the fact that z dz just multiplies by s. Sorry, I guess this whole left-hand side is just equal to, right? So if we sum up, we get a bunch of s to the j, which correspond to these terms. We get these qj of s, which are sort of, we actually want to keep those because those are elements of the ring that we care about. And then there's this dj or dz times z times f times zf to the s, right? And so maybe on this left-hand side, I'll recall, so like the commutativity rule says this is equal to z dz plus 1. So in terms of acting on this symbol here, in terms of acting on this symbol, this is just an s plus 1. We can move it with the f because they're sort of independent from each other. And so really we get an equality, oh my gosh, we get an equality sum of s to the j, s plus 1 qj of s times f times zf to the s. This is just equal to this b times zf to the s. And we have an isomorphism of d modules, or really of dxs modules. Right, because if we do a differential operator in the x's, it sort of doesn't do anything with this z term. The z will always just sort of pop out. And so I think, yeah, our isomorphism should just, it's really sort of some sort of evaluate z at 1. But we just let ps zf to the s map to ps f to the s. And so that is an s here. And so our equality in this ring, it only has coefficients in dxs. It gives us an equality in the ring that we care about. And so that implies that this b of s like satisfies the functional equation that we want. Yeah. And so we get the desired result. Yeah, I think like really we should just think of this as evaluate z at 1. Okay, so this is an interesting trick of Kashiwara to turn a general polynomial into a quasi-homogeneous one. And it sort of reduces it to that case of quasi-homogeneous polynomials. Okay, great. Okay, yeah, so now let's talk about, so yeah, here's where this like generalization of the result is. So we're gonna start talking about the shapes of the roots, some more general B functions. Right, so we can extend the action of this from, so it's on NF, to all of this ambient module R inverted F adjoint S times F to the S. But now it's an isomorphism. And I'm going to label this as BF tilde of F, or sorry, BF tilde. And so that means, well, yeah, we should keep in mind that it's an isomorphism now, but we can define for any U in this BF tilde, the B function of u is the, so non-zero monic polynomial of minimal degree in like complex polynomials with a single variable, such that bs times u is in this submodule. So this is contained in this bf tilde. Right, so for any element, we could talk about t times that element, and then we just look at the submodule generated by that. And we want a polynomial which multiplies the element into this submodule.
Sorry, Brad, could you remind us what the action of t is? What is t?
Yeah.
Thank you.
Sure, yeah. So t times ps f to the s is equal to ps plus 1 times f to the s. And so it's invertible because now we can divide by f, and we can also, the p times s plus 1, we could just shift by s minus 1. Okay, yeah. Great. So maybe an example is if we let u just equal this f to the s, then actually we recover this Bernstein-Sato polynomial. Yeah, so I guess we just recover bf of s. Right, and that's because, sorry, I don't want this to be the definition. I also want to allow action by the variable t here. Right, so recall that, yeah, right, so t acts on this whole thing, so we can really think of this as a dxst module. And so the right definition includes the action by t here. But what happens is when you're just multiplying by f to the s, all of the t action is just multiplying by powers of f. And those are captured by the dx term already, right? So even though it's like dxst times tf to the s, this is equal to dxs times f to the s. Because all of those t's are just giving us more and more multiples of f on this symbol, and those are captured by the dx action. And so we do recover the old definition. And maybe another remark is, right, how do we know that these b functions exist? Is actually these bu of s exist for all u in this bf tilde once we know that this bfs exists, and that its roots are negative rational numbers. I should say are in Q negative. And we're going to prove this parenthetical part, like that's what we're going to do today. But yeah, so basically the existence of a B function for any element is basically equivalent to the existence of the V filtration, if you've heard of that, on this big module. And there's a construction starting just from the B function for this generator f to the s to the entire V filtration of this module. So even though we've only proved existence for f to the s's B function, I think we can extend that to every element of this BF tilde. But it's sort of a complicated thing, and yeah, it involves this word V filtration, which we won't really talk about today. Okay, and now let's define something that will help us get some elements of interest. So, right, t is invertible, so define dt to be s, well, negative s t inverse on this BF tilde. So this satisfies so it's called dt, and it actually does act by, like, it has the right commutativity property with this element t, and also dt of s. So t shifts it to s plus 1, and dt, because there's a t inverse there, turns it into s minus 1. Yeah, and I guess I should say, like, dt commutes with all elements of dx. Okay, so our goal today, understand bu of s when u equals g times f to the s, or u equals dt to the m f to the s for some g in O of x, so in this ring R, and some m greater than or equal to 0. So I guess when I say understand, I mean understand the roots of. So we're going to want some sort of divisibility with a polynomial we can write down. And Kashiwara's idea is to use resolution of singularities to handle this. But you'll see that it's kind of, we have to do a lot of work to actually get information on a resolution down to the module that we care about. So let me just define what I mean by this resolution of singularities. So some map pi from y to x is a resolution of singularities of this 0 set f equals 0. If it is proper, which is like this, I think we talked about it last time. It was this, basically for us, it preserves coherence of D modules when we do this push forward operation. It's birational, which means there's some open subset on which it's an isomorphism. So if we throw away some closed piece down here, then pi restricted to that, the inverse image of that will be an isomorphism. And we'll actually be very specific on what open set we want it to be an isomorphism of later on. And if, okay, so I should say, right, we want to be able to, if we pull back this function f, right, so we're really just composing, f is a map from x to c, and so y would, or pi upper star f is a map from y to c. So this is locally, I'm going to be a little hand wavy on most of these things, but really the idea here is it's locally a monomial times a unit. So p times y1, a1, yn, an, where p is a unit on y. And if, right, we have these chosen coordinates. So if we look at this volume form, remember this comes up in the side changing operation. So this is the volume form on x. X, like we have these chosen coordinates, so this is okay. We can pull that back. So I'll just call that dx. Right, you can pull back differential forms. It sort of commutes with the d and the wedge. So you're really just pulling back each of these xi's. We can write that as h times locally these dy's. So when I said monomial, I mean sort of we have coordinates in this coordinate system, we can express this pullback as a monomial times a unit. And so sort of in that same coordinate system, we pull back the volume form and we write it in terms of those coordinates. And there's this coefficient here, h, where h is a unit times some other monomial here. So q is a unit on y. So not only do we monomialize f, but we also want to monomialize this thing, which is, it's called like the relative canonical divisor. Okay. And maybe just to fix, so these letters, we're gonna wanna like keep track of these k's. They correspond to this pulling back the volume, the differential form. These a's correspond to pulling back f. And then we'll just say like for this g and r, we'll write pi upper star g as g, and that's going to be some, I guess I called it sigma. It's not really important what the coefficient is, but I did want some letters for sort of the order of vanishing of g, the pullback along those coordinates. So here, sigma doesn't have to be a unit, but sigma is not divisible by the g or by the y's. Okay, so really this is just sort of, I'm trying to give like an idea of what this would mean locally, because we're really just going to be working locally. I think we need to be a little bit more careful, but this is really the gist, is that you can monomialize these two pieces, and up to not being able to pull out more y's, you have some monomial you can talk about when you pull back this function g. Okay, so why is this useful? So I'm going to leave this as an exercise / lemma. Right, so let's let F be, I'm going to ignore that unit part, the invertible element for now. So we look at this monomial, and G is y1 to the b1, yn to the bn. Then, okay, so 1, if u is equal to gf to the s, then bu of s divides. So we can be very explicit with what this b function looks like when we're just multiplying a monomial by another one. Bi plus j over ai. So this j goes from 1 to ai, and I goes from 1 to n, right? Hopefully that's legible. In any case, we get complete control over the roots in a sense that like we know a set which we can describe the roots as. The roots are a subset of things that look like negative bi plus j over ai, where those numbers come from this resolution data. And then 2, if u is dt to the m f to the s, then bu of s divides. So we kind of need this s plus 1 term here. Yeah, that part's a little bit tricky to see why, but I guess I'll still call it an exercise because I don't really want to explain it. It's the same product indices. And we just sort of, now we shift things. So there's no G to talk about, so there's no BIs, but there is that J, or that N. There we go. Okay, yeah, in any case, this exercise / lemma shows us if we're in the monomial case, we can actually compute these B functions in the sense that like we know what they have to divide. Remember, they're sort of minimal in a sense. So if we can show that there is a functional equation with this polynomial, this larger polynomial here, then the minimal one has to divide this biggest one. Okay, and then this is key to the following. This is the main theorem. So this is like, I mean, it encapsulates the theorem of Kashiwara and the theorem of Lichtin, but this is with my advisor, Mircea Mustatsa. Okay, so let's let F and G be in R, and we're still going to assume F satisfies this star. It's probably okay if we get rid of it because of this generic smoothness. But yeah, so if U is of the form G times F to the S, then that means every root of BU of S is smaller than the negative of this number. And 2, if U is dt to the m times f to the s, yeah, so every root of BUS is of the form. So m minus ki plus 1 plus l over ai. For some l, a non-negative integer, and one of the i's between 1 and n. Okay. So is the statement okay? So it's really just a hope. I sort of state it in this way because this is sort of the way that an application will be used if I have time to state the application. But here we get very explicit control over what the roots look like. And we'll actually see why we have to move by some non-negative integer later on, like why that L has to be there. So maybe a remark is if we let m equal 0 in 2, then that implies that every root of BF of S is in, so it's rational, and it's a negative rational number. So this is the original theorem of Kashiwara. Actually, I mean, because we have stated it with these KIs, this is really Lichtin's form of the theorem. He used side changing to bring into the formula these KIs, and we'll see how that comes up. Okay, Yeah, so I'm going to describe sort of the whole story of the proof starting now. Are there any questions before we get started on that? Okay, great. Proof. And so there will be
I'm sorry,
lemmas.
I have a question. Sorry about that. So what are these KIs in the main theorem exactly? I mean, these KIs might be different depending on the portion of the resolution you're looking at, right?
Yeah, so I think those KIs would really be if you pull back the divisor, you have these sort of exceptional divisors. And if you look at like those fixed exceptional divisors on the whole yeah, so I guess I'm cheating a bit because I wanted to state everything locally, but yeah, I guess you have to be more careful with what you mean when you're pulling out those numbers.
I understand. Yeah, thanks a lot.
Yeah, thanks for the question. Okay. So yeah, we're going to want to use D modules, of course. So I'm going to define some D modules. They look a bit gross, but the thing to keep in mind is that they're all generated by a single element over this ring here, dx adjoin S and T. And it looks like D T to the M F to the S. Right, so we could really prove things more generally for elements that look like this, but I think the statements are cleanest if we specialize to when M equals 0 or when G equals 1. And so I'm going to basically give the proof like this, but the computations are cleaner if you only think of it in one way or the other way. But I don't want to write out two proofs. I mean, it's really the same thing. Just imagine this isn't here or imagine this isn't here when you're reading the proof. Okay, and in fact, I'm going to be specific. So remember that NF was this NF0 adjoin, like with this 1, right? So this was dx st times f to the s. But like we said before, this is just dxs times f to the s. Because the t action gets absorbed when the f to the s, you just multiply by f, and that's part of the differential operators ring. Okay, and maybe just to be safe, I'm going to let NFM1 just be denoted as NFM. Okay, and recall that we had this translation of the B function in terms of minimal polynomials of the S action on some quotient. So really B, okay, G dt M f to the s is the minimal polynomial of the S action on, so NFMG mod T NFMG. Yeah, so this is why this is how we can talk about it in terms of just the D modules. But a warning, so like this is just like what happened last time. These are not necessarily coherent over dx, right? They're generated by a single element over this larger ring. Whoops. But it's unclear if you can like get the S and the T action just from differentiating. So yeah, I will do a remark though. So same definitions for those F and G, which are the monomialized versions. But actually they're quasi-homogeneous. And so at least we know that NF0 is coherent over dy, right? I guess, so I'm being sloppy here, but locally it's finitely generated because of this quasi-homogeneous assumption. We saw this last time. You get the S action from that operator that recognizes it as quasi-homogeneous. I mean, I really don't even need the G to be quasi-homogeneous, but yeah, and then coherence is just sort of a local property. Okay, so here's a lemma which is going to be useful for us. So whenever I do capital F, think of it as just a monomial. So NFM is dy by coherent and it's locally generated by these f to the s, dt f to the s, all the way up to dt to the m f to the s. Right, so actually we get something stronger. A priori, we don't even know that these elements lie in that module, but we'll see in the proof that they do lie in it and that they generate the module. And then we want some sort of structure on the characteristic variety. Right, if you remember, the proof of existence really came down to showing that the quotient was holonomic, because S was a dx linear endomorphism of the quotient, and so it had a minimal polynomial. So actually, holonomicity is going to be very important for us later on. And we get some control on the characteristic variety of these guys. So they actually have all the same characteristic variety, and we're going to denote that by WF, which is the notation that Kashiwara used. Okay. So the proof is not so bad. So remember that these things commute, they have this commutation relation. And so that implies if we look at the action of T on this thing, well, I guess any D to the J, F to the S. Right, so this is, okay, so really like this alone implies that dt to the J times T is equal to J dt to the J minus 1. You can prove this by induction, just using this initial commutation relation. And so that implies that the action looks like, right, so really this would be dt to the J times T f to the S minus J dt to the J minus 1 f to the S. But that first term, T times f to the S, is F, capital F times f to the S. So we can pull that out. Minus J dt to the J minus 1 f to the S. Yeah. And right, assuming we have dt to the J f to the S, and we can multiply by T and F, which we can do when we're looking at this ring dx S adjoin T, we automatically get dt to the J minus 1 f to the S. So that implies that those elements, so descending induction, implies that f to the S, well, maybe I'll do it in the other order. D to the m minus 1 f to the S, D to the m minus 2 f to the S, f to the S. These all lie in this NFM. And so now all we need is the S action, right? Yeah, also I should say, right, when you do this multiplication by T to the generator, that's in the submodule generated by the smaller powers and the differential operator action. So this allows us to absorb the T action once we know that these guys are contained in this NFM. Yeah, so we need the S action in terms of dy. Have I been writing? Yeah, okay. But remember, we had this commutativity. This was just dt to the m s plus m f to the S. Yeah, and we have, right, so this is, oops. This is equal to, well, this is in dt to the m dy times f to the S. Because of our quasi-homogeneity property, right? Because these are quasi-homogeneous, we get the S action by using that vector field that recognizes them as quasi-homogeneous. And so just by multiplying by that vector field and adding m, we get that S plus m f to the S. But then this is contained in NFM, oops, capital. Yeah, and so that completes the proof up to like probably writing it out more logically. But now we have this, by the first part, we have this collection of inclusions. So it's chain. So at least we get this. This contains this WF, which remember we were calling NF0. But we can look at NFM mod NFM minus 1. This is generated over dy by the symbol d to the m bar f to the S, right? If we just look at this list of generators, if we were to increase m by 1 or decrease it by 1, we would get all of these generators, but not this guy. So the quotient is generated by sort of the missing generator. But then that means we get a surjection of dy modules NF0 onto the quotient. Right, and so this would be like P S f to the s maps to P S d to the m f to the s. Right, since these are both cyclic over d of y, we really just need to see like if something kills the left-hand side, then it also kills the right-hand side. Right, this is sort of how quotients of cyclic modules would work. And so this is because if PS f to the s equals 0, well, I guess, yeah, I'm really talking about them as cyclic d modules, where P is in this dy, then P times dt to the m f to the s is equal to dt to the m P times f to the s, because dt commutes with the dy action. And so we get this quotient here. Oh, and then I should say, so that gives us a containment in the other way, is contained in WF. And then we use now regular increasing induction to conclude that they all have the same characteristic variety. So if you look at the short exact sequences, the middle one has the union of the outer two characteristic varieties. And if you can keep showing that the outer two are the same guy, then the middle guy has the same one too. Okay. This is actually pretty important because a lot of our logic relies on working with coherent D modules when we like push forward and want some finiteness. So that could be called like a key lemma. Okay. Now I'm going to state some properties of WF due to Kashiwara. So the first one is we could really write it as the closure of this set. It's not so important, but it does help you get a picture of what it should look like. S times df of y, where f of y does not equal 0, and s just varies in C. We take the closure of that inside of t star y. I guess I should, yeah, I'll call it t star y, but we were thinking of these just with some like trivialization. I'll do C to the n because that's what I've been writing today. So you get an explicit description of it. We're not really going to be so interested in the explicit description, but two, this WF is pretty easily, because of that description, this is irreducible of dimension n plus 1. Right here, n was the dimension of x and y because they have an isomorphic open subset, and it dominates y in the sense that if we do the projection, this is also not super important, but it's an interesting property, right? So we have WFS. The image is dense in y. That's what this domination means. And we can see that here because it includes every point where f of y is non-zero. So it hits that whole open subset. And yeah, y is an irreducible variety. So open subsets are dense inside y. And finally, this is actually the most important property. So if we look, right, we have this projection down to y, but if we look at the points that lie over the 0 locus, so they're sort of not given by this description. So they somehow arise from the closure operation here. This is an isotropic subset of this T star Y with its canonical symplectic structure. So I'm just going to say this is a notion from symplectic geometry. And it implies that the dimension is less than or equal to n, which is really useful for us, but it's more but it's like stable by an operation that we will use later. So we need this stronger version to actually, we're going to use it to conclude something has dimension less than or equal to n. And the operation we do later doesn't automatically preserve this property, but it does preserve the stronger property, which is what we're going to be interested in. Yeah, and we'll see the operation is a bit complicated, but this number 3 is sort of the important part. So we need a stronger version of having small dimension, and it comes from this notion from symplectic geometry. Okay, so now we will make these assumptions. So we will also assume pi, remember this is our resolution of singularities, is an isomorphism over this big open subset, I guess it's a small open subset, where f is non-zero. So this is called like a strong resolution. That will be important just so we can get a handle on the push forward of certain modules. And remember, we're always going to assume f satisfies this star, which was this thing that was like df dx1, df dxn. If we look at all the partials where they vanish, that's necessarily contained in the 0 set of f. Okay, great. And now this next section is this is like, so Lichtin's idea is to use side changing to get more information. Right, but we need to talk about side changing for these dx_st modules. This part is like, it's going to end up not really mattering because we're going to side change and side change back, and that sort of undoes the operation. But right, recall that s is equal to this negative dtt, right? The way we defined dt was it was negative s t inverse. And so that implies if we side change, so recall the side change operation was p, which is this sum of like p alpha x d to the alpha. This maps to negative d to the alpha p alpha x. And this satisfied like pq, this is called the transpose or the classical adjoint. So it interchanges the order of them. So because this looks like a differential operator times sort of another one of degree 0, we should really, when side changing, have s act by, so we interchange the order, so it should be t dt, right? If we swap which one's first and also negate this one, we get t dt, which is dtt plus 1 or minus 1, which is really, yeah, negative s minus 1. And so all of this is just like some sort of pedantic thing, which is to say, right, if we're looking in the side change module, so if we look in like nr, which is omega tensor n, and we have some element u tensor this dx in here, in n to the r, and we'll call this u star, then we get a relation bu star of s is equal to bu negative s minus 1, where this bu star is sort of minimal such that, so u star, bu star, right now we're in a right module. This should lie in u star times t times dx st, where now we want s to act sort of in this negative s minus 1 way on the u part. So this is just sort of like a pedantic step that we need to make to just make sure the theory actually works out well. But you can ignore it. It really, like, we change and then we change back at the end. So like doing this S maps to negative S minus one, it sort of undoes itself. So it's not very important, but if you want to know like the details, that's a step that we have to do. Okay, so now we consider the right D module, right? Right dy st module. So it's just we side change upstairs nfmg, and this has a global section. So in omega y, we can pull back the volume form from downstairs. So if we do pi upper star dx tensor, right, this was sort of a cyclic module over that. Do I name this? Yeah, I'll call this V, right? So we actually, this is where the extra information, this was Lichtin's idea, was to look at this thing, which has the relative canonical divisor sort of inside of it as some data. The nice assumption that we made that pi is an isomorphism over F non-zero will really mean that when we look at this element over that open subset, F does not equal 0. It is the same thing as dx, like up to a unit. So it really doesn't change anything on that big open subset, but it's very useful to get those numerical invariants into the picture. Okay, and we'll let M be the cyclic submodule generated by this thing. So that's contained in this omega y tensor n fmg. And we'll let B of S be its minimal polynomial of S action on M mod Tm. Well, I guess I should say MT. Okay. And so like by that lemma / exercise, we know like BS has like the desired form, like a nice form. Has roots that we understand, I guess I should say. And now the hard part is getting that we know these roots, getting that downstairs. And so that's what we're going to, oh, I should say, right. So remember, I'll just write down. So V is this pi upper star dx tensor g f to the dm f to the s. This was really that like unit times y to the k1, yn to the kn, tensor y1 to the, there's this guy, b1, yn to the bn, dt to the m. I'll just write y to the a to the s for like the shorthand. And we can tensor, oh, there's my u dy tensor sigma y, all right, y to the b plus k, dt to the n, y to the a s. Yeah. And so this was why in our the statement of the main theorem, we got b plus k terms. And it's because we included this pi per star dx in the whole picture. Okay, so I'm gonna have to go pretty quickly to finish this. Okay, so Tx injectively on this Bf tilde. So that implies it does on M2. Right, when you side change, you kind of don't really change this multiplication by regular functions so much. And so that means there exists a dy linear map from M to itself such that Bs is equal to T of phi, right? Basically an element, when you apply B of S to it, it's T times something, and that something we call like a function of that element. Yeah, and then recall from last time, because this pi is assumed to be proper, that this cohomology module is dx coherent. So we're going to use that, and that's because M is dy coherent. And that's because we're in the quasi-homogeneous case, because we have these monomial assumptions upstairs. So we can define S and T actions on H naught plus by, well, just H naught plus, so this is of M, sorry, that was of M, by this and by this. And they satisfy the same thing where T of S is S plus 1 of T. Okay. And so that means BS is equal to, if we just we apply H naught pi lower plus to this by like functoriality, and the way that we define the action on S and T, this is just H naught pi lower plus of var phi, or phi. And so that means that BS kills the quotient H naught pi lower plus of M mod H naught pi lower plus of M times T. So now we've moved our information downstairs. And yeah, something important was that there was a canonical section. So we like working with these cyclic modules. So what do? We have, okay, sorry, I'm going a little bit too fast here. Right, we have a map from OY to, okay, sorry, I'm getting distracted. We have a map from dy to m, which just maps 1 to that section V. If we tensor this, remember we had these transfer by modules, that's how we define the push forward. That gives us a map from dy to x to this m tensor dy to x. And remember, this thing was just pi upper star of dx, which has like a canonical element, which is pi upper star of 1 in here. And so if we let O of y map to that element, so 1 maps to that special guy here, we get, it's not really like a canonical section because this thing is an element of the derived category. But when we apply H naught pi lower plus to this, and we use that, this is something from like algebraic geometry. When you push forward the structure sheaf along this sort of proper birational map, you get back, and X is smooth, you get the whole structure sheaf here. We get a canonical section of this module. And I'll say that 1 maps to, should I call it W? W. Okay. So now we'll let L be the, I guess we're doing right D module. So this is the cyclic module generated by that element. Okay, sorry, we're almost done. I just want to finish sort of, yeah. Okay, we're not actually almost done. Yeah, there's like 1 more page of notes. So maybe I'll just skip a lot of things. Right, okay, so note. Pi is an isomorphism over that set where F is non-zero. And so that implies if we restrict L to the set where F is non-zero, we actually get an isomorphism of this with our NFMG twisted by omega x. Again, we have to restrict this to F non-zero. Oops. I should say this is sitting inside of this H naught pi lower plus of M. And also H naught pi lower plus of M restricted to F non-zero is isomorphic to this. So everything's really the same on that big open subset. And so that implies that this quotient, H naught pi plus M mod L, is, yeah, it's really supported on F equals 0. And then the claim is that this quotient, which I'll call M prime, is holonomic. And the proof is like, this is where we use the isotropic property. So use isotropic plus there's these canonical maps, T star Y, Y cross X, T star X to T star X. This is beta, this is alpha. This allows us to move the characteristic variety from T star Y into information about the push forward characteristic variety. So this is contained in alpha beta inverse of the characteristic variety of M, right? That was living upstairs. Pull it back to here, push it to this. And the fact that basically alpha beta inverse preserves isotropicness. So that's like a very hand wavy way of putting it. Or we're sort of out of time, but this is where that important property comes up. And this is the convoluted operation that I was talking about. Okay, great. So we have a quotient, which is holonomic. So basically it all follows from this lemma. If L is holonomic with a dxst action, then that implies that there exists some k in Z such that t to the k L equals 0. So proof, I could show you the proof if you asked me about it, but because I'm really out of time here, I'll just show how this gives us the divisibility that we want. So this lemma implies t to the k times that quotient, mod L is 0 for some k. I'll say greater than or equal to 0. So that really means that t to the k h naught pi plus m is contained. I really want it to be on the right-hand side because these are right modules. It's contained in L. So if we do it one more time, that's contained in L times t. Okay. And yeah, so L times bs times this whole product, bs minus k, is contained in this h naught pi plus m times bs minus k, which is contained in this thing t to the k plus 1, which is contained in L times t. So finally, we get that at least the b function of L divides this big product here. Okay, and then finally, L surjects onto N, F, M, G. Yeah. This is basically because we're on a strong resolution. So yeah, because pi is an iso over F not equal to 0. And so finally we get our desired divisibility. Okay, and I'll just say, sorry for going so far over time. This K was Y in the statement of the main theorem. There's this ambiguity of that extra L. If I look at the shape of the roots, where's the main theorem? Here. This L here, and I guess the reason why this is less than or equal to, that L is coming from the fact that we don't really have control over which power of t killed that quotient. So the best we can say is that there is some K such that if we do all of this stuff, I might even want those to be plus K. I'm gonna write plus K because I think that's probably what I want. Probably, I'm actually not sure, but okay. Yeah, so maybe one more time. Okay, so that will finish the talk. I'm sorry I went so far over. I think I was going a little slow in the beginning, but thank you so much for listening.
Are there any questions for Brad? So I have a kind of vague question that following this approach, is it ever possible in examples to just by analyzing the resolution to understand the roots completely, or is that kind of hopeless?
You mean like understand the roots in sort of this exercise lemma, or you mean like when you
well for a more interesting F, right? So for something other than a monomial, if you understand the resolution of singularities well enough, is it can you, rather than just come up with this list of candidate roots, can you ever nail them down completely?
I'm not sure, because I think like along the way there's a lot of divisibilities that come up, and I guess it might be hard to actually say when the divisibility is an equality, or like when you can show which roots get thrown out when you look at a quotient or a submodule. Yeah, like I think I probably really glossed over that, but yeah, we start with something upstairs, we push it forward, and we can show that the B function divides when you do the push forward. So already you lose some there. And then we look inside of that at a cyclic submodule. So there's some divisibility, but maybe not necessarily equality here. And then finally, it surjects in this last step onto our desired module, which is again going to lose like a little bit more information on the exact form of the polynomial.
Okay.
Yeah, I think it's hard. There might be a way to get more like constraints on it, but I don't really see a way. Yeah.
Okay, thanks.
Yeah, thanks for the question.
Of course, yeah. Any other questions? Okay, well, if not, yeah, let's thank Brad again for a couple of nice talks. Good, yeah, and so next week we'll be off. There's a workshop at ICERM, so if people are interested in more D modules talks, then yeah, then join us in ICERM, and then otherwise we'll resume here in a couple of weeks.